We've seen a number of different tools for solving quadratic equations, from factoring to using square roots to completing the square. All of these are useful in their own way, but no one of these tools can handle every quadratic equation. Turns out that the tool we will look at today does handle all possible quadratic equations. It's called the quadratic formula. I'm not going to take the time in this lesson to build the formula for you. We're just going to jump right in, talk about what the formula is, and then show how to use it. Now, before I get started with it, let me just answer one question. You might be thinking, well, why didn't you show me this in the first place? Well, that would be a good question to ask. And the answer really is that the other tools that we've already seen have really good uses in their own way. I would hate for you to just have this one tool to solve all the possible questions on all the possible quadratic equations you're going to see. And this quadratic formula, although extremely useful, can be a bit cumbersome at times. So the other tools that we've already seen really are useful. Now, with that said, let's talk about this quadratic formula. Here's exactly what it says. If you start with an equation of the form ax squared plus bx plus c equals 0, where a, b, and c are just some real numbers, then the solutions of that equation are exactly given by this. X equals negative b plus the square root of b squared minus 4ac, all divided by 2a, and x equals negative b minus the square root of b squared minus 4ac over 2a. It's that simple. And you say, simple? That looks really complicated to me. And I wouldn't blame you for saying that sort of thing. In fact, for some students, it's extremely hard to memorize this formula correctly with all of those letters floating around. If this is the first time you've seen the quadratic formula, I don't blame you for being a bit hesitant. But the beauty of it is that it provides a surefire way of solving any quadratic equation that we can write down. Now, you should definitely spend some time putting this thing in your memory banks. It's an excellent tool for what I like to call our algebra toolbox, and you really want to know it well. Now, let's start by solving a quadratic equation for which we actually don't need the quadratic formula. But by solving it with the quadratic formula and also solving it some other way, I'll be able to check to make sure that I've done the problem both ways correctly. So let's try this first. Let's solve this equation, x squared minus 11x plus 28 equals 0, and let's solve it first by factoring. Okay, we want to find the values of x which make this equation true, and the first way I want to do it is by factoring the left-hand side of the equation. So I'm going to write down x squared minus 11x plus 28 equals x minus 4 times x minus 7. Did you get that factoring? I hope you did. Now, we've seen that already. We know how to factor. And now it means that my original equation can be rewritten as x minus 4 times x minus 7 equals 0. We then know from the rules we've seen in the past that we can split that product into two equations and write them as x minus 4 equals 0 or x minus 7 equals 0. And that simply means that x equals 4 and x equals 7 are my solutions. And I'm done. I could check those answers by plugging them back into the original equation if I wanted. But instead of checking it that way, I'd like us to redo this problem, not with factoring, but with the quadratic formula. And then if we get the same answers, we'll be very confident that we have the right solutions. So let's go back to the original equation. X squared minus 11x plus 28 equals 0. If I want to use the quadratic formula, I have to be able to make sure my equation is in the form ax squared plus bx plus c equals 0. So what are the values of a, b, and c in this example? Well, the value of a is 1. Remember, there's a 1 in front of that x squared. It's just that we don't typically write it down. What's the value of b? It's negative 11. Don't lose that negative sign. It comes along in the value of b. So b really is negative 11. And the value of c is just 28. It's positive 28. Then the quadratic formula tells me that the solutions are given by the following. X equals the negative of negative 11 plus the square root of negative 11 squared minus 4 times 1 times 28, all divided by 2 times 1. That's one solution. And the other one is the negative of negative 11 minus the square root of negative 11 squared minus 4 times 1 times 28, again divided by 2 times 1. Now, those look messy right now, but once we get into the practice of it, simplifying these things isn't so bad. So let's practice by simplifying the first of these a bit, and let's see what we get. We have x equals the negative of negative 11, which becomes positive 11, plus the square root of negative 11 squared minus 4 times 1 times 28 divided by 2 times 1. That means x equals 11 plus square root of 121, that's the negative 11 squared, minus 112, that's 4 times 1 times 28, and the denominator is just 2, because that's 2 times 1. And now this cleans up even more. X is now 11 plus the square root of 9, because 121 minus 112 is just 9, all divided by 2. The square root of 9 is just 3, so x equals 11 plus 3 divided by 2, or 14 divided by 2, or 7. Wait a minute, 7 was one of the solutions we got a few minutes ago. That's fabulous. So what looked really messy at first, just a few moments ago, actually worked its way down and simplified to just the number 7. Now, let's try the other solution. Let's make sure that it simplifies to the right value. So the other solution that the quadratic formula tells us we have is x equals the negative of negative 11 minus square root of negative 11 squared minus 4 times 1 times 28 divided by 2 times 1. And that simplifies to 11 minus the square root of negative 11 squared minus 4 times 1 times 28 divided by 2 times 1. And now this simplification starts to feel a lot like the one we did a moment ago. We now have 11 minus square root of 121 minus 112 divided by 2, or 11 minus square root of 9 divided by 2, or 11 minus 3 divided by 2, which is 8 divided by 2, which is 4. By the way, now that we've done one set of those, I want you to notice that those simplifications actually felt a lot like one another. So you'll start to see some commonalities as you're working through the two solutions from the quadratic formula, and it should speed up your work just a bit. Now, did you notice that that x equals 4? That was the other solution that we found a few minutes ago with the factoring technique that we used. So we've now seen that factoring and the quadratic formula gave us exactly the same answers, and that gives us confidence that we're on the right track with this quadratic formula. Now, I'd like to move to a second example, just the same idea really quickly, although we're going to complicate it ever so slightly by wiggling the original equation just a bit. Here's the example I want us to do. Solve the equation x squared minus 7x minus 14 equals 5x plus 10. Now, the first thing we need to do before we ever get started with this problem is to get the equation in standard form, which is just a fancy way of saying that we need to move everything over to the left-hand side so that the only thing on the right-hand side is a 0. So if I start with my original equation, x squared minus 7x minus 14 equals 5x plus 10, and I subtract a 5x from both sides, and I subtract 10 from both sides, and I simplify, I'm going to have x squared minus 12x minus 24 equals 0. Now, notice that what we're left with now is a quadratic equation. There really is an x squared there, and because of that, we know that we can use any of the tools that we've been learning about in the last few lessons. You might want to try to factor this, but guess what? It's not going to work in this case. Take my word for it. If you try factoring that equation, you'll be there a long time because it's not going to be as clean as the factorization we saw a moment ago in the previous example. So, instead of trying factoring, let's attack it with the quadratic equation instead. Now, in the notation of the quadratic formula, we need to know what A and what B and what C are. And in this example, A is going to be 1 again, because there's just a 1x squared. B is going to be negative 12. And C is going to be negative 24. Don't forget to include those negative signs with any of these numbers. As long as the number in the equation was negative, then we need to make these numbers with the quadratic formula negative as well. Now, plug in everything and simplify. In fact, I would suggest right now you stop the video, plug in those values, try this yourself, and see what you get. Okay, now the solutions of this equation are going to be x equals negative b plus the square root of b squared minus 4ac all over 2a, and x equals negative b minus the square root of b squared minus 4ac over 2a. And we already know that a is 1, b is negative 12, and c is negative 24. So the first solution that we're going to have is the following. X equals the negative of negative 12 plus the square root of negative 12 squared minus 4 times 1 times negative 24 divided by 2 times 1. And that simplifies to x equals positive 12, because negative of negative 12 is positive 12, plus the square root of negative 12 squared minus 4 times 1 times negative 24 over 2 times 1. And that'll clean up quickly to x equals 12 plus square root of 144 plus 96 divided by 2, which is x equals 12 plus the square root of 240 divided by 2. Now, you might stop there, but actually you can go a bit further, and I'd like us to simplify this as much as we can. So let's look at that square root now for just a second. Notice that 240 is the same as 16 times 15, or you could think of it as a 4 times a 4 times a 15 if you'd like. And 16 is a perfect square. So, using some of the rules that we've seen in previous lessons, we know that square root of 240 is the same as square root of 16 times 15, which is the square root of 16 times the square root of 15, which is 4 times the square root of 15. And now, in the simplification I had done a moment ago, I can replace square root of 240 by 4 square root of 15, because they're the same thing. And that means x equals 12 plus 4 times the square root of 15, all divided by 2. And if I factor a 2 out of that numerator and then cancel that 2 with the 2 in the denominator, I'll have x equals 6 plus 2 times the square root of 15. That number is one of the solutions of the original equation. And you should just put it to the side now. It's an important value because it is one of the solutions. But now I want us to go simplify the other solution that we're going to get from the quadratic formula. So let's do that next. We know that we have, in this second solution, x equals the negative of negative 12 minus the square root of negative 12 squared minus 4 times 1 times negative 24 divided by 2a. That's a lot to say, by the way. It's long, isn't it? But we can work through it. Just take it step by step. That means x is 12 minus the square root of 144 plus 96 divided by 2, if we just do some of the simplification quickly. Notice that that looks a lot like the other solution. Earlier, we had 12 plus the square root of 144 plus 96 divided by 2. And now let's simplify further. We know we have x equals 12 minus the square root of 240 over 2. We learned that the square root of 240 can be rewritten as 4 times the square root of 15. So this x is 12 minus 4 times the square root of 15, all divided by 2. And again, factoring a 2 out of the numerator and canceling it with the 2 in the denominator gives me x equals 6 minus 2 times the square root of 15. Now, I want you to notice that the two solutions here are almost the same. They're almost identical. They actually only differ in the sign that's sort of in the middle. And some people like to write these solutions as 6 plus or minus 2 times the square root of 15. It's perfectly fine to do that, but sometimes for some students, it hides the fact that there are actually two solutions there and not just one. So if you want to write the solutions with that plus and minus symbol in it, it's not a problem. Just remember that that is showing really two solutions and not just one. Now, at this point, I'd like to look a bit at the algebra itself and define one of the most important vocabulary terms related to quadratic equations. You may have noticed that a bunch of the simplifying we had to do occurred under that square root symbol, or under the radical symbol, as some people call it. And because of this, and because that amount that's under the radical symbol is so important, we have given it its own name. It's called the discriminant. So we're going to define the discriminant of the quadratic equation ax squared plus bx plus c equals 0 as the quantity b squared minus 4ac. And that's the amount that's under that square root symbol in the quadratic formula. So you might wonder, well, who cares? Why is this discriminant so important? Well, one reason is very easy to state. The sign of the discriminant immediately tells me how many real number solutions the original equation has. You could say it in a more graphical way if you wanted. The sign of the discriminant, whether it's positive or negative after you've simplified it, tells me how many x-intercepts there are for the parabola, which is given by y equals ax squared plus bx plus c. Notice in the example that we just did, the discriminant was exactly the 240, positive 240. And because the discriminant is positive, immediately I know that the parabola that's related to that equation has two x-intercepts. In fact, you can look at a quick sketch of that graph, of that parabola, which shows us pretty quickly and pretty easily that there really are two x-intercepts. And actually, we could say a bit more. We know where those x-intercepts are. They are at 6 minus 2 times square root of 15 and 6 plus 2 times the square root of 15. And if you get a calculator out to estimate those, you'll see that the first is at negative 1.746 or so, and the other is at 13.746 or so. And if you look at the picture, that is pretty much where those two x-intercepts land. All right, let's look at another example now, and I want to see if we can solve it using the quadratic formula. Here we go. Solve the equation 9x squared plus 4x plus 8 equals 6x squared minus 4x plus 11. Okay, the first comment is, wow, that's a really ugly equation, and I would agree with you, but let's just move everything over to the left-hand side to get it in standard form, and then we'll see what we have. What we have when we subtract or add everything over to the left-hand side and simplify is 3x squared plus 8x minus 3 equals 0. Now, I don't know about you, but I don't even want to start trying to factor that. I mean, we could, and we could spend some time trying to think about it, but now that we know the quadratic formula, and hopefully some of us are getting comfortable with it, I say we just use the quadratic formula. In this case, the value of a will be 3, the value of b will be positive 8, and the value of c is negative 3. And that means if you just plug that information into the formula, the solutions are x equals negative 8 plus the square root of 8 squared minus 4 times 3 times negative 3, divided by 2 times 3, because the a value is 3. And the other solution is x equals negative 8 minus square root of 8 squared minus 4 times 3 times negative 3, all divided again by 2 times 3. Let's simplify that first solution now. It's going to be negative 8 plus the square root of 64 plus 36, all divided by 6. Notice that we got a plus 36 there because we took minus 4 times 3 times negative 3. And that all simplifies to x equals negative 8 plus square root of 100 divided by 6, And the square root of 100 is pretty straightforward. It's just 10. So we have x equals negative 8 plus 10, all divided by 6, which is 2 over 6, which is 1/3. And that's not such a bad solution. Okay, it's not a whole number. It's just a nice friendly fraction, though. X equals 1/3. Well, what's the second solution? Well, again, we go back to that quadratic formula, and we have the following. X equals negative 8 minus square root of 8 squared minus 4 times 3 times negative 3, all divided by 2 times 3. Don't forget that 3 that's in the denominator, because a equals 3. And you'll have x equals negative 8 minus square root of 64 plus 36, all divided by 6, which is x equals negative 8 minus the square root of 100 over 6, which is x equals negative 8 minus 10 over 6. That's negative 18 over 6, which is negative 3. So the two solutions in this example are x equals 1/3 and x equals negative 3. So even though we started with a pretty ugly equation, the solutions aren't so bad. In fact, let me just make a couple comments here. One is that original equation, after we had simplified it and put it in standard form, really could have been factored. But okay. But a second comment to make is, look at the graph of this equation. Y equals 3x squared plus 8x minus 3. Do you see where the x-intercepts are, the two places where the graph crosses the x-axis? One of them is clearly at negative 3, or it's certainly very close to it. It really is at negative 3. And the other one is at 1/3. And so those two x-intercepts are given to us as the solutions of the original equation. And one more comment. That discriminant, you remember? The value under the square root sign. What was it? It was 100 before we did any simplification of the square root. We had square root of 100. So the discriminant itself is just the 100. And since 100 is positive, we knew that we had two x-intercepts, or two solutions to the equation. Now, here's a good question you might want to ask. Can the discriminant ever not be positive? I mean, come on, you've shown us several examples now where the discriminant was always positive. Well, in fact, that's a very good question. The discriminant sometimes can be something other than positive. So, let's look at an example where that happened. Let's solve the equation x squared plus 12x plus 36 equals 0. And let me give you a quick task to do. Why don't you start by calculating the discriminant for that equation? Okay, the discriminant here, remember, is b squared minus 4ac. That's the quantity that's under that square root in the quadratic formula. B in this case is 12, and a is 1, and c is 36. Well, let's calculate this discriminant and see what we get. It's b squared minus 4ac, which is 12 squared minus 4 times 1 times 36. And when you simplify that, you get 144 minus 144, which is 0. Wait a minute, 0, that's the discriminant, and in fact it is. That's not positive though. Remember, 0 is not a positive number, it's also not a negative number. So that means that something different might be happening with the x-intercepts of the parabola we could draw that corresponds to this equation. And in fact, that's exactly right. So here's an important fact to remember that's motivated by this example. When the discriminant of a quadratic equation equals 0, so it's not positive and it's not negative, it just equals 0, then the corresponding parabola has exactly one x-intercept. And that means, if you want to think of it this way, the parabola just sits right on the x-axis, either from above or it might be coming from below. It doesn't really cross it so much, it just sits there so that there's only one x-intercept. In fact, if you look at the original equation that we started with, x squared plus 12x plus 36, I can rewrite that as x plus 6 whole thing squared equals 0, using a little completing the square from a previous lesson. And we know that there's only one solution of the equation x plus 6 squared equals 0, and that solution is x equals negative 6. We could find that using our square root tool from a previous lesson. And that means that the graph of y equals x plus 6 squared only has one x-intercept. Well, you and I know know that already because the graph of x plus 6 squared is exactly the graph of x squared, just shifted to the left 6 units. And both of those graphs, x squared and x plus 6 squared, simply sit right on top of the x-axis. So this graph looks like this, just sitting right on that x-axis. One x-intercept because the discriminant is exactly equal to 0. Now, I've shown you an example where discriminants can be positive. I've shown you several of those, in fact. And I showed you this very unique example where the discriminant was exactly equal to 0. And now I'd like to show you one more example where the discriminant is something else. You can probably guess where we're going to go with this. Let's try the following example. Solve the equation x squared plus 7x plus 15 equals 0. And let me give you a quick task again. Why don't you calculate the discriminant first and see what you get? Okay, the discriminant, remember, is b squared minus 4ac. In this example, a equals 1, b equals 7, and c equals 15. And those are the values we would need for the quadratic formula or just for the discriminant by itself. Let's calculate that discriminant. B squared minus 4ac is 7 squared minus 4 times 1 times 15, which is 49, minus 60, which equals negative 11. And now this example shows us a third thing that can happen with the discriminant. It could be negative. And now we need to interpret what this means. Well, first of all, it means that the quantity that's under the square root symbol in the quadratic formula is negative. Okay? Now, are we allowed to have a negative number under the square root symbol? Well, if you only want to deal with real numbers, then you cannot have a negative number under that square root symbol. And that means that the original equation, in this example, x squared plus 7x plus 15 equals 0, has no real solutions. Okay? So that's the first important point to make. The second one is that if you think about the parabola for just a second, and you think about how many x-intercepts it has to have 0 x-intercepts because the equation itself had 0 solutions. And that means if the parabola has 0 x-intercepts, it means that the parabola never, ever touches the x-axis. It either lives above it the whole time if the ends go up, or it lives below it the whole time if the ends go down. In fact, if you want, you can make a quick sketch of the graph of x squared plus 7x plus 15 just to confirm that the graph misses the x-axis the whole time. Now, as we close today, let me recap what we know thanks to the discriminant, which is part of the quadratic formula, when you're dealing with an equation like ax squared plus bx plus c equals 0. First, remember the definition of the discriminant. It's the amount b squared minus 4ac. And that's the quantity that's under the square root symbol in the quadratic formula. Okay, that's the first thing to remember. Secondly, we know that the sign of the discriminant, whether it's positive or negative, or maybe 0, tells us something. If the discriminant of the equation is positive, then the equation will have 2 different real number solutions, and the corresponding parabola will have 2 different x-intercepts. If the discriminant of the equation is exactly 0, then the equation has only 1 real number solution, and the corresponding parabola will have only 1 x-intercept, so that the vertex of the parabola is just sitting right on the x-axis. And thirdly, if the discriminant of the equation is negative, then the equation will have no real number solutions, and the corresponding parabola will have no x-intercepts, so that it misses the x-axis completely. Now, one other thing can be said here. Even though that original equation has 0 real number solutions when the discriminant is negative, it still has 2 complex number solutions. Just remember to use the fact that the square root of -1 equals I and go from there. So if your teacher or an exam wanted you to find all the solutions and allowed for complex solutions, then that negative discriminant wouldn't be a problem. You would just find answers which are complex. Now, let me encourage you to practice using the quadratic formula several times in order to nail it down. There's a lot going on in that formula, and it often messes students up. Where's the A? Where's the B? Where's the C? Pluses and minuses and so on. So be careful and practice it as much as you can. Next time we'll do a bit more with quadratics, but instead of talking about equations, we'll talk about inequalities that involve quadratics.